All right, we're going to get to it here, a problem where we're going to solve for the concentration at equilibrium. So for the reaction, there's our reaction right there. Nitrogen gas and oxygen gas are going to form nitrogen monoxide. We have an equilibrium constant of 0.16. And we're starting with an initial concentration of nitrogen and oxygen gas at 1 molar. So our nitrogen and our oxygen gas are going to have an initial concentration of 1 molar. And since it doesn't say anything, I'm going to assume my nitrogen monoxide has 0. And so I don't need to do an equilibrium quotient for this question. I can predict that this equilibrium is going to shift this way because there's none of this, so it's going to have to create some of it at its equilibrium condition. To solve this problem, I'm going to use my ICE chart. Initial, change, equilibrium. And I'm going to make sure I've written my balanced chemical equation across the top so that I remember my ratio between my different changes. If my nitrogen is decreasing to create some nitrogen monoxide, I'm going to say it's decreasing by a factor of x because I have a 1 coefficient on the nitrogen in the chemical reaction. I'm going to say the oxygen is also decreasing by x, and then as a result, since for every one of those and one of those I make 2 of these, this is going to increase by a positive 2x. What that then means at equilibrium is the new concentration of nitrogen will be 1 minus x, the new concentration of oxygen will be 1 minus x, and the new concentration of nitrogen monoxide will be 2x. So with K in hand, 0.16, I have my concentration of my products, NO squared. Oh, all of these are gases, by the way, so they're all going to get included in this equilibrium constant. I have my concentration of my nitrogen and the concentration of my oxygen, both to the power 1. So now at equilibrium, I can put in these expressions for the concentration at equilibrium and solve for x to figure out how much change occurred in this system. I could square this out and do the quadratic and it'd work out and it'd be a little annoying, take a little bit of time. Or I can recognize a neat little trick in this example. Specifically, this is a perfect square, this is a perfect square, and this is just a number. So I have a little trick here I can use to solve for x. I can square root both sides, and it's going to make my expression a lot easier. Just to make sure that's clear, I'm going to rewrite this. 1 minus x on the bottom here could be rewritten as 1 minus x squared. And so I can see that I can square root all of these entities easily. Doesn't happen very often, but when it does, it solves you multiplying the whole thing out and finding the quadratic and doing that whole thing, so this is convenient. Okay, so the square root of 2x squared is just 2x. The square root of 1 minus x squared is just 1 minus x. And the square root of 0.16, pretty sure is 0.4, yep, 0.4. Now we can solve for x. 0.4 minus 0.4x, bringing the binomial up. 2x, and then bringing the minus 0.4 to the other side, it becomes 2.4x. 0.4, dividing both by 2.4 then. And my x works out to be 0.16666. I'll just go 667, that's fine. So the question actually asked for the concentrations of the particles at equilibrium. So to get the concentrations, I need to substitute this x value that I found, or the amount of change that I found, into these 3 expressions. For the concentration of nitrogen gas, it happens to be the same as concentration of oxygen gas. So that's 1 minus x, or 0.833. The concentration of nitrogen monoxide happens to be 2x, which will work out to be 0.333. So the equilibrium will shift. Some of the nitrogen gas will get used up, some of the oxygen gas will get used up, some nitrogen monoxide will be produced until we reach these new concentrations, at which time the forward reaction rate and the backward reaction rate will become constant and the two things will stop changing.